Welcome to this lecture. Today we are going to start a new topic that is related with the finite difference formulations of differential equations. So differential equation could be ordinary or it might be partial differential equation. So as you know, differential equation, they model a continuous phenomena. And when you want to solve this problem on a computer, then you need to transform differential equation into difference equations. So then you are at the discrete level. So the first thing you need to have is the representation of, or you could say transformation of derivatives to their discrete versions. That is finite difference. So I will start with the first order derivative du by dx. So at location x equals to xi. So this is the first order derivative. So to approximate this, we apply the forward difference approximation. This can be approximated as u of x plus h minus ux divided by delta x. This is through Taylor series plus order delta x. So could also write like ui plus 1 minus ui divided by delta x. So this is the stencil. This is the location I. This is location I plus 1. So du by dx at x equals to xi. This is approximated by this difference approximation. Similarly, we could have backward difference approximation, which is ui minus 1 divided by delta x. Of course, this is again order delta x approximation. This is through Taylor series, very basic. And this is at x equals to xi. This is xi, this is the location I minus 1. This gap is the delta x. And last is the central difference approximation of first order derivative. So now we will move in both directions. This is the location I, the location or node or grid point I plus 1, the grid point located at I minus 1. So du by dx at the location I is u at I plus 1. What is the value, functional value at the neighboring node, future node minus the past node, the previous node, and now you can see the gap would be 2 delta x. So you have included both the directions. Of course, this is a better approximation. This is of the order delta x square. Again, you can see this through Taylor's series approximation. So for a first order derivative, we could have three formulations: forward difference formulation, backward difference formulation, and central difference formulation. So if you want to have approximation of second order derivative at the location x equals to xi, how to proceed? So again, if you expand u forward and backward at the location x, This will be u of x plus h u dash of x plus h square by 2 factorial u double dash x plus h cube by 3 factorial u third order derivative plus this, and u of x minus h u dash x plus h square by 2 factorial u double prime x plus negative x cube by h cube by 3 factorial. So let us say this is Taylor series 1 to 2. What is our target? We want to find expression for the second order derivative. So if we add these two expressions, the first order derivative will be cancelled out. So you would be having u of x plus h plus u of x minus h twice ux plus twice h square by 2 factorial u double prime x, and this will again be cancelled, plus dot dot dot. So this 2 is cancelled by this. So u of x plus h plus u of x minus h. You can have this on left hand side 2ux is equals to h square u double dash x plus of the order h cube. Okay. Now we have ux plus h plus u of x minus h minus 2ux divided by h square is equals to u double prime x. Sorry, here could be order h4 because order h cube term has been cancelled out. So if you take common as h square, so here now you will be having order h square terms. Because if you take h square common from all the terms and you divide on the left hand side, so the order h4 term is now reduced to order h square term. So in the form of indices, so u double dash x are the second order derivative of x at the location I. In the form of indices, this would be u of I plus 1 plus u of I minus 1 minus 2ui divided by h square or delta x square, whatever you want to write. And this is order h square approximation. So summary, first order derivative, forward approximation ui plus 1 minus ui divided by delta x at I location. Backward difference approximation, the value of the function at the ith grid point minus the previous grid point by delta x. This is again order delta x approximation. And better one is the central du by dx at I ui plus 1 minus ui minus 1 by delta x twice plus order delta x square. And for second order derivative, we have ui plus 1 minus 2ui plus ui minus 1 over delta x square plus order delta x square. Now we have to transform all these expressions into partial derivatives so that we can apply these into finite difference approximations of PDEs.